Alright, so today we're going to talk about something that's a little bit more abstract than probably anything else you've ever seen in math before. We're going to talk about finding complex roots of functions using imaginary numbers. Now, you guys have never seen imaginary numbers before, so I'm going to introduce it. Hopefully I'll do it slow enough so that it makes sense. And you'll also get that summary at the beginning of class, so that'll help as well. What's going to be a little tricky is you can't visualize imaginary numbers very easily. We'll talk about how to graph them in a couple days, but there's no really good way to envision what it would look like to have an imaginary number. So you just kind of got to go along for the ride. So we're going to find complex roots. Remember, roots are where a graph passes through the x-axis. We're also going to find complex points of intersection, which is going to be a little strange, and you'll see why in a little bit, but basically that just means that your graphs don't intersect in a real solution. So, the first thing we have to talk about is what's an imaginary number. Now, we've never seen these before. So, the place that this comes from is when we're talking about roots that don't exist, essentially. And it came from when we take the square root of a negative number. You always used to get to this point here where you got to like the square root of -1. And for example, you couldn't take the square root of -1. And so you would just say, we don't have any solutions. There are no solutions. Which makes sense. If you look at this graph up here, there's no place that this graph crosses that x-axis. So we're looking at the function y equals x squared plus 1 that has no x-intercepts. So what I did on the top here was I'm trying to figure out my x-intercept, so I set y equal to 0. And then I gotta subtract 1 from both sides and take the square root. So I get x equals plus or minus. Remember, when you take the square root, you get plus or minus the square root of -1, which we don't know how to do. But so that we could have a solution to this problem, a long time ago, we created this thing that we're going to call I. Now, if you look here, I've written that I equals the square root of -1. So I is essentially our imaginary number, square root of -1. Now, if I take that right there and I square both sides, I get -1 equals I squared. Now, make sure you have those two things in your notes. That's going to be super important for our use of imaginary numbers. I'm going to give you some examples of how you might use imaginary numbers. So, for example, the square root of -16. I can take -16 and split it up into 16 times -1 underneath that square root. Then I can take the square root of 16, which is 4, and I can take the square root of -1, which is I. We just defined it on the last page. Okay, so all you've got to do is split up the number from the -1 when you've got the square root of a negative number, and then that square root of -1 is always going to give you I. Let's look at another example. So the square root of -4, I split it up into the square root of 4 times -1. The square root of 4 is 2, and the square root of -1 is I. Now I can also take this and I can go the other way. Remember we said I squared is equal to -1. So if I'm multiplying 2I times 3I, I multiply 2 times 3 to get 6, and I times I to get I squared. Now I squared was defined as -1, so I can replace that in this step, 6 times -1, and get -6. We'll try another one that's kind of like that. We've got 2I squared times -5I. The first thing I'm going to do is I'm going to take this 2I squared, I'm going to square my 2 and square my I. That's how I get this step. I got 4I squared. Now, I'm replacing I squared with -1. Okay, so 4 times -1 times -5I. All I'm going to do is multiply 4 times -1 to get -4. And then -4 times -5 gives me positive 20I. Go back and look through those steps again. If I lost you, go back and look through that and see the little steps that I was taking. And the last example is kind of like the first two that we did. The square root of -25 is the square root of 25 times -1. The square root of 25 is 5. And the square root of -1 again is I. Make sure you have all of these examples written down in your notes. They'll help you a lot. Now we're going to talk about finding complex roots. Well, we haven't gotten to what a complex root is. We'll get to there at the end of this example, but it has to do with imaginary numbers. So the first thing I want to do in this example is find the roots of the function y equals x squared minus 4x plus 5. And I drew a little picture of what this graph looks like. If you type that into your calculator, that graph will give you a picture kind of like the one that I drew there. And if you'll notice, it doesn't have any real roots. There's no place where that graph crosses the x-axis. So I'm going to try to solve it algebraically. And I'm going to set my equation equal to 0 so that I can figure out where it crosses that x-axis. Okay, so since I can't factor this nicely, obviously, since it doesn't cross at nice points, I'm going to use the quadratic formula. So I set a equal to 1, b equal to negative 4, and c equal to positive 5. I'm going to plug that into the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So I replace all of my variables in there with the numbers that I already found and work it out as you see there. Notice that when I get to the step where I just stopped my drawing, I have 4 plus the square root of negative 4. Now that's the part before where you would always stop and say, okay, there's no solutions, I can't do this, I can't take the square root of a negative number. Well, now you know how to find the square root of negative 4 using imaginary numbers. Remember, you split up 4 and negative 1. The square root of 4 would be 2, and then the square root of negative 1 would be I. So I get 4 plus or minus 2i divided by 2. Now I divide 4 by 2 to get 2, and I divide 2 by 2 to get 1i. Okay, so all I'm doing is simplifying 4 divided by 2 and 2 divided by 2. That gives me my roots. Now obviously when I write these, I'd have to write it as 2 plus I, comma 0, and 2 minus I, comma 0. That's how you would write your roots. The definition of complex roots is a real number plus or minus a multiple of I. So you'll notice here I've got 2, which is a real number, and I've got plus or minus just 1i in this case. It could be plus or minus 3i, 4i, whatever you want to do with that. But a complex root, the definition is that real number plus or minus some multiple of I. So make sure you get that down in your notes as well. Now, on your notes on the back, I want you to do an example of this. It's really important that you're practicing this right now. Look at that example I just gave you, and then try and do this one on your own. So please pause the video and give it a try. I want you to find the complex roots of the function y equals x plus 3 squared plus 4. Now you'll notice that this is a parabola just like the last one, shifted up 4. You can tell from what we did last chapter that my k value shifts this graph up by 4. What you need to do is to expand that x plus 3 squared and then use the quadratic formula to solve it. Okay? Give that a try. Make sure you have that. Come with any questions to class on Monday. The last thing we're going to do before we call it quits on imaginary numbers for today is talk about points of intersection that are complex. So if two graphs don't intersect, then the solution to that system of equations is going to be complex. Just like if we don't have real roots, we're going to have complex roots. Same idea here. If we don't have real points of intersection, we're going to have complex points of intersection. So I've got the system of equation, y equals x squared, which is that parabola, and y equals 2x minus 5, which is that line. And I drew them on the graph, and you notice they don't cross. Okay, and they will never cross in our real set of numbers. So what I'm going to do is I'm going to set those two equations equal to each other. Since they're both equal to y, I can say x squared equals 2x minus 5. Then I'm going to get everything onto one side of my equation so that it's equal to 0, and I can use that quadratic formula. I'm going to work it out in the quadratic formula the same as the last time, and you can look through my calculations. But I get to this point where I get 2 plus or minus the square root of negative 16 over 2. Now I have to simplify that square root of negative 16. I get 2 plus or minus 16 times negative 1 over 2. I take the square root of 16 to get 4, the square root of negative 1 to get I, and then I just divide 2 divided by 2 to get 1, and 4 divided by 2 to get 2. Okay, so I'm just taking that denominator, splitting it up, and simplifying my fractions. So I've got two x values that would be complex points of intersections, 1 plus 2i, and 1 minus 2i. Now to find a point of intersection, you know I have to have x comma y. So I've got to take both of these x values and plug them back into one of my original two equations. So I'm going to take this x equals 1 plus 2i and plug it back into that second equation. So I'm going to plug it back into 2x minus 5. And all you have to do is distribute that 2. So 2 times 1 is 2. 2 times 2i is 4i. Okay, and then minus 5. And then just combine your like terms. With imaginary numbers, combining like terms is the same as if that was a variable. So you can't combine that 4i with 2 or negative 5. You could only combine it with other terms that had I in them. Okay, so when I combine that, I get a point at 1 plus 2i, comma, negative 3 plus 4i. And if I went back into that again with my other x value, I would have 1 minus 2i, comma, negative 3 minus 4i. I went through that kind of fast, okay? But if you pause the video, go back and look through the work, there's nothing there that's algebraically that tough. And what I want you to do now is on your own, look at my example that I just did, hold it right next to your paper, and in your notes, solve this system. So set the two equal to each other, and then multiply both sides by x. Get everything equal to 0, and then use that quadratic formula. Okay? Might help to draw yourself a picture so you can see that these lines aren't going to cross with real solutions. Okay? So do it with that example that I just did right next to it, solve this on your notes, and come to class with specific questions on Monday that you have. I want to see that you at least tried it before you quit. You guys are totally capable of doing this, and I look forward to having a conversation with some of you who are watching this on Monday.